Hello, for today's video lecture, we're going to be talking about the equivalent point load via composite parts. So as a reminder, the equivalent point load is a single point force that is statically equivalent to some original distributed force. So it would cause the same acceleration and angular acceleration as the original distributed force if the object is left free, or it would cause the same reaction forces as the original distributed force if the object is constrained. So this is a single point force that is statically equivalent to our distributed force. So finding this via composite parts, this is the alternative to using integrals. So we can use the method of composite parts to find the magnitude and position of our equivalent point load. So we are looking for FEQ, the magnitude, and XEQ, the position of our equivalent point load for this simple distributed force on a beam. This is going to be a geometry-based solution rather than calculus-based. So if you can use this method, it's usually faster than doing the moment integrals. All right, so as we stated before in the integration page, the magnitude of the equivalent point load, FEQ, is going to be equal to the area under the force function. So we can find the area under the force function by doing an integral, but we can also sometimes say, well, the area under the force curve here is just a trapezoid. If I know the area of our trapezoid, that is the magnitude of the distributed force. So the widths in this piece, so the width of our trapezoid is going to be in units of meters in this case. It's going to be some unit of distance. The height of our force function was in this case it'd be newtons per meter, but it's going to be some force per distance. And so if you multiply a distance by a force per distance, the overall area is going to be a unit of force. So it's going to be newtons, it can be pounds, etc. All right, so next up is the position. So XEQ can be determined by knowing that the equivalent point load will always travel through the centroid of the shape under the force function. So I'm not going to go through the whole process of finding the centroid, but if you look in Appendix 2, you can see more on finding the centroid of a shape. So the centroid of this force function area is going to be basically XEQ. So the X location of the centroid is equal to XEQ in this case. All right, so if we jump to surface forces, so say we've got some force distributed over X and Y, it's much the same process. So the magnitude of the equivalent point load is now just the volume rather than the area under the force function. And the equivalent point load will still always travel through the centroid of the volume under the force function. So in this case, we're going to need to find two of the three positions of the centroid, so X bar and Y bar, but that will be equal to XEQ and YEQ. So if we're able to look that up, we can do that. If we can use method of composite parts to find that centroid, that works as well. All right, so that's all we have for today's video lecture. Thanks for watching, and I hope to see you again.